this case again 2 cross 1. X and y coordinate, that is all you need of this point, this particular point. Okay? And the output is going to be another vector, another matrix of 2 dimension again, 2 cross 1.
Then to understand the transformation as a whole, we might imagine watching every possible input vector move over to its corresponding output vector. It gets really crowded to think about all of the vectors all at once, each one as an arrow. So, as I mentioned last video, a nice trick is to conceptualize each vector not as an arrow, but as a single point, the point where its tip sits. That way, to think about a transformation taking every possible input vector to some output vector, we watch every point in space moving to some other point. In the case of
so again you can think from one coordinate like one matrix to the another whenever you are thinking about the dot. Dot means again it is having the x and y coordinate. After some transformation, what would be the new coordinate? Okay? Just so that you can understand what is happening, if I have in one image a point at 2 cross 2, 2 comma 2 or 2 2, and then I just move that object 1 unit to the right and 1 unit to the up, what will be the new coordinate? 3 comma 3. So, the translation that happened is what? 1 comma 1. So, that is the idea we will see, but I am talking about only one point, but things could be more complicated, right?
Transformations in 2 dimensions, to get a better feel for the whole shape of the transformation, I like to do this with all of the points on an infinite grid. I also sometimes like to keep a copy of the grid in the background, just to help keep track of where everything ends up relative to where it starts. The effect for various transformations moving around all of the points in space is, you've got to admit, beautiful. It gives the feeling of squishing and morphing space itself. As you can imagine, though, arbitrary transformations can look pretty complicated. But luckily, linear algebra limits itself to a special type of transformation, ones that are easier to understand, called linear transformations. Visually speaking, a transformation is linear if it has 2 properties. All lines must remain lines without getting curved, and the origin must remain fixed in place. For example, this right here would not be a linear transformation, since the lines get all curvy. And this one right here, although it keeps the line straight, is not a linear transformation, because it moves the origin. This one here fixes the origin, and it might look like it keeps lines straight, but that's just because I'm only showing the horizontal and vertical grid lines. When you see what it does to a diagonal line, it becomes clear that it's not at all linear, since it turns that line all curvy. In general, you should think of linear transformations as keeping grid lines parallel and evenly spaced. Some linear transformations are simple to think about, like rotations about the origin. Others are a little trickier to describe with words. So, how do you think you could describe these transformations numerically? If you were, say, programming some animations to make a video teaching the topic, what formula do you give the computer so that if you give it the coordinates of a vector, it can give you the coordinates of where that vector lands? It turns out that you only need to record where the 2 basis vectors, I hat and j hat, each land, and everything else will follow from that. For example, consider the vector v with coordinates -1, 2, meaning that it equals -1 times I hat plus 2 times j hat. If we play some transformation and follow where all 3 of these vectors go, the property that grid lines remain parallel and evenly spaced has a really important consequence. The place where v lands will be -1 times the vector where I hat times the vector where j hat landed. In other words, it started off as a certain linear combination of I hat and j hat, and it ends up as that same linear combination of where those two vectors landed. This means you could deduce where v must go based only on where I hat and j hat each land.
So this is a very important part of the whole linear transformation. The only thing you are actually doing is to the basis vector. To the I and j, if you make it if you can transform that one, in respect to that, all other points would move accordingly. Okay? In this example, what is happening? My I and j was, I was here, j was here, and after that, this is the transformed j and the transformed I. Kind of the rotation and also kind of that shearing. So that is happening. Okay, two things together. But right now, so if you just make those things like scale only these two things, all other points will move accordingly. You do not need to think about that. So only modification you are actually doing is actually to the I and j, not to the real coordinate. In other way, if you think. Okay, only the modification is happening to the unit vectors.
This is why I like keeping a copy of the original.
So this line -1 is as it is, 2 as it is. All I am doing is transforming the I and the j.
Grid in the background. For the transformation shown here, we can read off that I hat lands on the coordinates 1, -2, and j hat lands on the x-axis over the coordinates 3, 0. This means that the vector represented by -1 I hat plus 2 times j hat ends up at -1 times the vector 1, -2 plus 2 times the vector 3, 0. Adding that all together, you can deduce that it has to land on the vector 5, 2.
Okay. Okay. Now just so that I can get you got it or not. At the beginning, what was that I bar? How can I write this? 1, 0. That would be the representative of the 1, 0. Right now it got transformed to the 1 minus 2. J was 0, 1. It got transformed to 3, 0. Okay.
This is a good point to pause and ponder, because it's pretty important. Now, given that I'm actually showing you the full transformation, you could have just looked to see that V has the coordinates 5, 2. But the cool part here is that this gives us a technique to deduce where any vectors land, so long as we have a record of where I hat and j hat each land,
again stopping. AC is what? Transformed of I, and BD is transformed of J. Not AB and CD. AC, BD.
Interpret that first column, AC, as the place where the first basis vector lands, and that second column, BD, as the place where the second basis vector lands. When we apply this transformation to some vector xy, what do you get? Well, it'll be x times AC plus y times BD. Putting this together, you get a vector ax plus by, cx plus dy. You could even define this as matrix vector multiplication when we put the matrix on the left of the vector like it's a function. Then, you could make high schoolers memorize this without showing them the crucial part that makes it feel intuitive. But isn't it more fun to think about these columns as the transformed versions of your basis vectors, and to think about the result as the appropriate linear combination of those vectors? Let's practice describing a few linear transformations with matrices. For example, if we rotate all of space 90 degrees counterclockwise, then I hat lands on the coordinates 0, 1. And j hat
would go to minus 1, 0.
lands on the coordinates negative 1, 0. So the matrix we end up with has columns 0, 1, negative 1, 0. To figure out what happens to any vector after a 90-degree rotation, you could just multiply its coordinates by this matrix. Here's a fun transformation with a special name, called a shear. In it, I hat remains fixed, so the first column of the matrix is 1, 0.
What is that second one? 1, 1? 1, 1. But here the fun thing is, for the shear, if I try to make it a little bit less, one axis is same, another axis is rotating like that, right? It could be a little bit less, not exactly like that, 45 degree. Then what would happen? It could be any value. There is 1, 1. The next thing, this x axis should be always 1. Y axis could be less than or more than 1, whatever you are choosing. So, it could be any scalar value. So, most of the time we will write it in alpha for that. We will not put a 1.
Over to the coordinates 1, 1, which become the second column of the matrix. And at the risk of being redundant here, figuring out how a shear transforms a given vector comes down to multiplying this matrix.
Oh, what we said? We told wrong, right? So, if my vector goes like that, then y is going to be 1, x is going to be any random number. So, alpha 1, usually, in this case it is 1, 1, but if I just make it anything, right? So, alpha 1, that is the shearing operation in this axis. Okay, clear? Oh, sorry, no, alpha 1, right? Your x is going to be, y is always 1. Yes. So, x axis I am not doing any changes, y axis was like that. I am just telling you, I want to make the y axis here. So, here it is still 1, but this thing x got some value, alpha 1.
By that vector. Let's say we want to go the other way around, starting with a matrix, say with columns 1, 2, and 3, 1, and we want to deduce what its transformation looks like. Pause and take a moment to see if you can imagine it. One way to do this is to first move I hat to 1, 2, then move j hat to 3, 1. Always moving the rest of space in such a way that keeps grid lines parallel and so the origin remains fixed. Delightfully, these transformations can be described using only a handful of numbers, the coordinates of where each basis vector lands. Matrices give us a language to describe these transformations, where the columns represent those coordinates, and matrix vector multiplication is just a way to compute what that transformation does to a given vector. The important takeaway here is that every time you see a matrix, you can interpret it as a certain transformation of space. Once you really digest this idea, you're in a great position to understand linear algebra deeply. Almost all of the topics coming up from...
So that is the idea. Is it now, did you get a better understanding than before? Yes? No? Or can you then turn on the light? So we need this information for computer vision. Turn on the light. For computer vision, because here also all the things, like, okay, as you can see, I can take a photo like that, and next time I can take a photo like that. What happens? Everything whatever in the image, something they got moved. Little bit rotation, little bit translation. So how, if you have those things, how can you model those? So modeling means kind of getting the transformation matrix. You want to just know the transformation matrix. If you can come up with the transformation matrix, whatever point is there in the image, you can just find corresponding where you can find the other image, other point, right? See, the features we are getting, the features are not going to give me all the points, it is going to be some set of points. So our idea would be then, from those feature points, come up with the transformation matrix, and if I have the transformation matrix, then I can just find out any correspondence to any point with any point. Clear? So for computer vision, this is very important part. Okay. So right now we are talking about the fitting, and we are talking about that for fitting, all we try to do is find the parameters of a model that best fit the data. For in this case, for a linear transformation fitting, all we are actually looking for a 2D fitting, not going to the 3D, not a perspective fitting. That means I am just want to the 4 numbers A, B, C, D. That's all I want to fit. Clear? Good. Now there are multiple ways of doing it. So, but mainly we need to see how good is the fit and how can we optimize. That means, okay, you come up with some fit, how good is that, and if it is not good, how can we make it better. Okay. So multiple algorithms. We will talk about some list square fit. All of you probably are aware of this one, right? So we will go through that. Other parameter search methods, and another model we already have learned actually, which is the generalized half transform. There also it is a model, but in a different way. You just do not set any parameter, rather you just give it a grid, and based on that you just try to see which grid fits better. Optimization is a little bit different, and then we are going to learn a new algorithm which is called the ransack. So simple example, let us start with a simple example. Fitting a line. We will try to fit a line with the least square method. How is it that done? How that is done? Linear regression, but I give you some point. Right, so you just come up with any random line, whatever you can think about, and then find the error. Minimum of the square, square root of SSC, yeah. Square, sum of square error, yes. Right, so that is, but you can also do it mathematically too.
So there is no closed form formula, F transpose F.
Exactly, very good. So there is a closed form formula for that too, for line fitting, right? Okay, so that is the exact idea. So all we are going to do is, if I give you this point x1, y1 to x and y1, these are the points. You just come up with a line equation, y is equal to mx1 plus b, a model, right? A model you have come up with, and then you find out the error is this. Okay. For each point you are saying what is the error, this is the sum total of the error. Once you find the error, Now this we are talking about the linear algebraic terms. So that means this term I can write it in this way. Okay? And if I can write it this way, that means I can write it in this way. Okay? And that means I can write it in this way. A is this, P is this, and Y is this. So this is the form we actually would always use to like, right? And you can see whatever points I had, this is a linear transformation, and I am just deducting minus Y. Y is the output that you are expecting, that you have actually, right? Clear? And what is the P? What is P here? The parameter M and B, and that is what you want to learn. So kind of three things: this, output, and what is the transformation? In other way, you can think what is the transformation that you can apply. If you can apply that one, your fit is correct. Okay. Okay, so and if you just continue and you can just do the differentiation, you can get this one, and from there you can get the pseudo inverse of this, and this is going to give you the result. So you are going to get the P. Clear? So you can get the P in a closed form without anything. Good? A and Y is both coming from the data. Nothing else you need to do. This is the easiest way of doing it, least square root. But now it has a big problem. What is the problem? It is closed form, so it should be very good, right? And it is totally mathematical, like okay, you're just doing a pseudo inverse, a linear algebra line. Like you can just do one line and it will give you the fit. What is bad in this? Actually, there is nothing bad, but one very bad thing is the outliers. Right now, our main problem actually is a defined one. What is the bad thing? The bad thing can I may have some matches which is not really a correct match. It is wrong match. We'll show you some example. Like okay, some points are literally on line, in line, but some point is there in some random places. Now your model, because it is a closed form one, it will try to fit that one also. Okay? Because the algorithm does not know where really the point is, right? So it is a good thing, clearly specified objective, optimization is very easy, just a closed form one. What is the bad? May not be what you want to optimize, because you may want to really get a line that goes through the most of the points, but not because sensitive to the outliers. If a bad match, it is going to cost you points. Any outliers is devastating for this algorithm, least square, okay? And of course, you cannot get multiple fits. So that problem would be there. So what is the example? Let's see. So if I have these points, nice beautiful points, if I just do this algorithm, run this algorithm, linear multiplication, just one multiplication, in a pseudo inverse, you are going to get a nice fit. But now if I have a point like that, this is what is going to happen. Only one outlier. And if I try to fit the line is not going here, it is going here, because now your algorithm need to take care of this point also. You want to minimize the yes. So prediction error. So because you want to minimize the error. So this is the best fit that you can come up with. So no, that is not a good idea. Okay. So yes, that's what we are going to learn today. Okay. That is what we are going to learn today. Okay. So other parametric search methods are what? Like the line search and the grid search. This is just for the completion. Line search is like you will just start with one parameter and you will see okay which and just go right and left to that parameter, increase that, decrease that, keeping other parameters fixed, and whichever value gives you the best result, you just fix that one, then you pick the next parameter, again go up and down and keep on doing it as long as you do not get the good fit. Iterative method. Grid search is propose several set of parameters, evenly sample in the joint set, kind of the grid idea, and then try them. Which one is giving you the best result, you just go for that. Okay? And third one is like the same thing as the voting. No, no, it is a different one. Here, like you just come up with your own set of M and B for this line fitting thing, and you see which one is gives you the least error. Okay, and then the other is the gradient descent, which is, how many of you do not know about gradient descent? All of you know, right? Gradient descent. Why did you learn? Machine learning for your CS. Huh? You don't know. But in AI also you covered. How can you don't know? Yes, in the AI course we went through that. Yeah, you know, right? No, all of you know, right? Good. So no excuse. Gradient descent is nothing. You just go through the direction of that against the direction of the maximum changes. So AI also you have covered, ML also you have covered. So you have, if you have taken either of these two courses, of course you have seen. So you did not take any of these two courses. Okay, now. So you don't know what is gradient descent. Okay, you do not need to know for the time being. Okay, it's kind of the idea is you just see the gradient, the direction where if you kind of take the derivative and it will give you the direction. Okay, if you go into this direction, your error is going to maximize. So all you are going to do is you just try to go to the other direction little bit at a time, and you keep on doing it as long as to see, okay, if the error is decreasing, that is good. Keep on doing it, and in this way kind of it will get the optimum. Okay, function minimization. Parameters and the errors, yes. Calculate the gradient. See, the idea is the same, right? So the idea here is the same thing. So you get the E, and then you take the derivative of the E for both the M and B. If you take the derivative, where you will get the 0? Like you take the derivative and take the 0. So at which direction it is the maximum? It will get the direction at which is maximize the error. Then all your task is to go in the other direction. Going in the other direction is very important. You do not need to go to the same direction where your error is increasing, right? You have to go in the other direction. That is gradient descent. Okay, but we do not need gradient descent much because we will see some other algorithm here. Okay, but you should know. We do not need for right now, but you should know what is gradient descent. We probably will cover a little bit later also if we need, if required. Okay, but now more important is our generalized half transform. We have talked about that every point is going to vote. Okay, I can fall into this line. That part is covered. Huh? That is generalized half transform. For our case, it is even more generic. It is a line fitting algorithm. You have some points. Each of these points is giving vote. That is literally a line detection algorithm using half transform. For any other problem, it could be generalized half transform, right? But it is a voting idea. Each point is going to give vote. You are not coming up with a grid and picking the values from there. Rather, here each point is giving some vote. You are just looking for the majority, right? But now, okay. But the most important algorithm that we are going to learn is today is called the ransack. Okay. What does the ransack stand for? No, that is a different algorithm. You can either choose this or you can go to choose this. Hypothesis test. So wait. No, that's correct. So what I'm telling you wrong. Generalized half transform. You find the parameter, then you test. Yes, right. So we just do the voting for each point. So I just take the vote for this parameter. That's correct. Yes. And ransack also works in the same way. You can come up with the model and you then see which one is working best. Okay. No, it is a combination actually, hypothesis and test. So in this case, it is one idea and this is one idea. So don't mix this with this. You are doing both things. You are giving a like you are just telling, oh, my aim could be this, this, this. This is your hypothesis, and then you just do the testing. Okay, is your hypothesis correct or not? You can do it in this way mathematically or with some known data and come up with the conclusion. And here you are providing your own assumption, and from there you are checking that okay, is it correct or not. Okay. You are just guessing, correct. Absolutely correct. Okay. So ransack. So ransack algorithm, we will see that okay, this is actually beautiful algorithm but very simple. Okay. And here also kind of the voting part would be important. So what is ransack? Ransack is called the random sample consensus. And if you see the algorithm, this is so simple and so intuitive actually. All you are going to do is you have these many points, you want to fit a line. Okay. All you do actually is just sample randomly. No need to see what is happening. The number of points required to fit the model. In this case, for fitting a line, how many points do you need? 2. Just pick 2 random points. You do not need to be okay the perfect one. Take 2 random points. And then solve for model parameters using samples. So if I have these 2 points, I can solve a model parameter for that. Okay. And then I have to see, I just need to take a threshold kind of, okay, how many, I cannot just fit all the other points may not fit exactly on that. So I will just take a threshold and we will see how many points fall into this zone. How many points? 1, 2, 3, 4, 5, 6. 6 points is coming into this zone. Out of what? Out of this many points. So this is my score. No, like that's what we will see. So there is no guarantee, but it will see probabilistically how this could work, how this would work. Okay.
After how much means it may happen that we are not getting not even close to the best fit.
So right, exactly, but it is only one sound. So now you have to repeat 1, 2, 3 until the best model is found with high confidence. So the last line is important. We are going to see that. This is clear? So as you can see, this probably is the simplest algorithm. You know there is a sorting algorithm like that? No. That is called BOGO sort. All you do actually is you have many points. You just randomly take all the points and you tell okay, this is the correct one. And then you check. So this is kind of the same idea. Bogus, from there it has come. That is a sorting algorithm though. So if someone asks you to write any sorting algorithm, you can always write that. So there is no guarantee that it will ever converge, you will ever get the correct one, but there is a good algorithm though. You might be very lucky. What is the best case runtime? BIGO guys? Constant. You might be extremely lucky and it is correct at the very first shot. So it is kind of the same idea, but it has some guarantee. Because first of all, you are just picking. So here why this is a little bit more guarantee is because of this thresholding. You are picking one and then people are giving vote. This is kind of the vote. Scored by the fraction of the inliers within a preset threshold of the model. Right? If you come up with some line and many other points are telling, oh, that is a good line, then this is going to be the winner. But very important thing, as you are telling correctly, so it is very important how many times I want to iterate this thing. Okay? Is there a fixed number? Clear? This algorithm should be very clear to all of you. Clear? Very good. So let's proceed then. Then repeat 1, 2, 3 until the best model is found with high confidence. There should be some way to measure the confidence. Yes. Right. So, we will see. So, once okay. So, in this way you will keep on repeat and it will at this point you found out that if you take this one, if you take the threshold, you can see that all you are getting a point like that, right? And you just conclude that because the n1 is 14, earlier one was how much? 6, what is the 6 written? 6, and it is 14, and if you see the other, you will see that this is the winner, so you conclude, oh, this is malign. But luckily you will get that one, right? You want to guarantee that. Your algorithm, you want to guarantee that, okay, with high probability, it is not like 100%. If you are extremely unlucky, you will never find that good one. You may try for 1,000 times, but still you may not get the correct one.
You can do one thing. You can rotate the line like this, 360 degrees.
Which line? So that you cannot do. So this you want to keep the algorithm simple. If you rotate that, now it might not be the correct one. It could be in another angle. This algorithm, we are talking about the line, but this algorithm is so generic that you will use it throughout this course. So your algorithm is what it matters, but not okay. We are doing it for line fitting, but it is not always the line fitting. For example, for the linear least square, right? The least square model we have seen. There also we are fitting how many parameters? 2, m and b, but it could be used in so many other places. The only thing that would happen is the number of model parameter will get changed. Machine learning, whoever is taking, doesn't matter if you have not taken, but you know that okay, it can work on any algorithm, any hyperplane or anything, any polynomial fit, right? So that is the idea here also. We are just fitting the line just for simplicity, and for the line I need to just fit 2 models, two parameters. So that's the only thing I need to sample. Sample the number of points required to fit the model. Based on the problem, this would get changed.
But in case of line, it may not necessary that the fitted line pass through 2 given points.
The fitted line pass through the
2 given points, but it may not be so. The best fit may not be passed through 2 given points.
very good. So in that case, the answer cannot do that, but most of the time that is okay. Most of the time that is okay, because if this is not the best fit, probably it will look ideal fit would be probably right that, but you cannot get that one. Here there should be some there is a word, what is that called? So those points must belong to the model, at least at 2 points. That is actually a loophole or a problem of the RANSAC. Okay. For example, if you have just point like this, right, and then you probably would like to fit a point like that, but RANSAC cannot do that. It will probably come up with something like that. Okay. So now the question is number of samples. How many samples do you want to get? And let's see. So multiple things you need. One is, so if I ask you how many samples do you want to how many times you want to take sample, how many times you want to take samples, right? The more I take, the better it is. The less I take, the more risky it would be. But now if I ask you, okay, I want that whatever number of sometimes you are taking the sample, after that 95% the probability would be 95% or more that there would be at least one sample which would give me the best perfect fit. So I have to probably repeat this way. So in this example, probably this is only 2 times I have done. How many times I have taken the sample? How many? 2. So 2 things are there. One is the model parameter, which is we are going to talk about the S. Another is the N. N is the how many times I am taking the random samples. N here is 2. Probably if I had first time I got 6, next time 3, next time 8, next time 14. How many times I have taken the sample? 4 times. Every time actually I am taking 2 points, 2 samples, sorry 2 points, but no 2 points I will say. So, these 2 samples are different. How many points I am taking? How many number of points I am taking? For a particular sample, that is fixed. That depends on the model, how many points or how many parameters you want to fit. How many numbers of samples? So, whenever you are talking about the samples, think about how many times I am taking this pair of points. Okay? Clear? So, multiple things you need. One is, okay, so this is number would vary. So, if I know the number of outliers is high, then should I need to take more points or less points? Outliers is high, then more number of samples or less number of samples? Outlier means, you know outlier? What is outlier? Extreme values, which are probably not part of the model. If those types of points are high, then what do you expect? Take more samples or less samples? More samples, very good. Okay. If we will talk about that also, if I find out that for fitting a model, I have a model which has more parameters, then do I need to take more samples or less samples? More parameters to fit. More samples, good. Now another thing, there is 2 component. Another component is the threshold. How big you want to, like, okay, every point is giving vote, right? How big you want to keep the threshold? You want to keep it very big or narrow? If it is very big, then more samples or less samples? Less. If it is small, then you need to take more. Okay? These are the ideas. Nearest neighbors, we are not going to calculate the nearest neighbor here, they are just giving the vote. Okay. But yes, but of course the nearest neighbor and distance are having very close connection anyway. Okay. So, how many numbers you want to take it? This is the number. Chena lage? Chena lage tobu ochena. Okay, so what is the S? S is the number of sample points. What is the E? Is the outlier ratio. Huh? Outlier means, okay, you might have 20% outlier, so it will be 0.2. Okay. So, let us solve this one. Should we solve this one? Sure, I think yes. So, how did you come up with this math? So, let us see. Just think, let us do this one, okay. Just think that I am taking a sample. That means I got some points. How many points? S number of points. Okay, and all of those points are outliers. So, all points, you should write this thing too. 1. Like no, like outlier, like okay, the sample you have taken, they are all points are outlier. What is the probability? You have, but what is the number? Outlier ratio is E. That means out of your total point, 100 points, you have E number of probably. If E is 20.2, then 20 points are outliers. I am right now taking that. If I take a sample, that means I am going to pick S number of points, out of that what is the probability that all the points are outlier? Hmm? E to the power S. Hmm? You take one point that is an outlier, what is the probability? You take only one point that is an outlier, what is the probability? A. You take S point, all of those are outlier, what is the probability? E to the power S. So you take one out sample and all of those things are outlier, probability is e to the S. Okay? Coming in? Sampling 2 point. Here S is 2, yes. S is 2. Right. You should have another formula. What happened to that? Okay, so you take one sample E, so if you take S sample, it will be S. So all points are outliers, what is the probability? E to the power S. Okay? All points are outlier, e to the power S, so and what about the all points are inliers? What is the probability of that? 1 minus e to the power S here or outside? Outside. Okay? You can see this is coming from that term. All points inliers is this. So take one sample, one points are inliers is this. Remember, for a good fit, we want all points are inliers. For a good fit, if I found out one point is on inliers, then of course the output, the error would be less, so I would be happy. But now think that some bad thing can happen. You can just think about that at least one point is outlier. Think about that case. Which case? The linear, the line fitting we are doing with the least square error. There one point was bad and that made my whole fitting bad. Okay? What is the probability of that? 1 minus E minus 1. S minus 1. Why is that? Why do I need to do anything with the 1? Is huh? Simpler than that. Very good, yes, 1 minus this. Everything is bad, that means 1 minus is that there will be at least 1. There could be there could be all points which are outlier too, but there will be at least one point which is outlier. Okay? I got this part. Clear? Very good. We're doing basic probability, but we will see that how we are coming up with these terms. Now, is it a good case or bad case? At least one point is outlier. Hmm? Good case. At least one point is outlier. Is it a good case or bad case? It's a bad case because only one time I want that there is no outlier. Right? At least one point is outlier, so this is a bad case. Next thought. Next, outlier. I'm going kind of at least one point is outlier. This, so at least minus power n. So this is, all these things are happening for one sample. Okay, one sample. That means one random pick. One random pick. This is happening. A bad thing happened. Okay. Now the same bad thing. So that means what happened? I just took 2 points and found one point is outlier. This is a probability. At least one point is outlier, right? Next time I took another point, one point is outlier. So I am talking about only one point, one sample I took, and there I found out there is an outlier. What is the probability of that same thing happening n times? All the consecutive n times. N times is the number of times I am taking the sample. To the power n. To the power n. Okay? So the bad thing happens this many times, all the n times. You want this probability, we are fixing the probability. You want now this thing, now all you want actually, you want this value kind of, if I write the equal to right now for the time being, equal to, like okay, n times you took, all the n times is bad. You want this probability to be more or less? I want it to be less, right? And I want it to be less than probably 3%. Okay, for example, 3%. That means I want my probability 100 minus 3, 97% I am correct, right? So that if the p is the probability of correct, then I just need 1 minus p. P is the number that how many the probability that with 90% or 97%, 95, like quite a high number. That means that percent of the time that if you take this, there will be at least one sample where there won't be any outlier. Okay. For example, if you want it to be better than 97%, that means you want this number should be less than 3%. Okay. So if you want from this line, you can just take some log and everything, because all you want right now, all you want actually is this, calculate this n. Okay. P is the probability that everything is correct. P is the probability that this is the probability we want that if you take n number of samples, then with that p percent what is it, p with p probability you will find at least one match, but there is no error, because if there is no error, that is going to get the maximum vote. That means you are going to get the correct fit. Okay. From this line, if you do the other log, then you will just going to get the result. Okay. So from there you can calculate the n, and it will come like that. You need to take the log, because if you take the log, n will come here, and then you just need to fix that part. Cool. Okay. So you got the n. So this is the formula of the n. N should be greater than this number. Okay. You can do this math at home, no problem with that. But now this n, there are two main components here. You can see that the threshold is not coming here, because threshold is something that is depending on you. The threshold is telling you you are flexible or you are very rigid, but that is not part of the formula. Okay. But this threshold actually based on the threshold also the probability is kind of gets reflected. The probability is also depends on this threshold. Why? Because how should you tell that? Based on the error model, how bad is your data? If the data is bad, your probability would be anyway less. So you want to take like how you want to make this threshold more or less. That's kind of depends on the model itself. If the data itself is bad, your probability should be less at the very beginning, because you know that you are not going to get the correct. Probably you are not going to get the correct fit. So your probability expectation would be less. Okay. But now more important thing is this. Now you can see how many parameters are there in this n. I have E and I have S, and this is for a particular P. So P is fixed. If you want the 90% accuracy, then your P is fixed, you have the S and you have the E. Now if you know that the growth of the algorithm, which one is for the point 2 for when the S is 2, which is for the line fitting, portion of the outliers is E outliers, E having more is better or less is better? Less is better, because that means all the points are fitting the model. So there will be less chance of error. So if it is 5%, I need to take 2 points, 10%, 3 points. In this way, for 50%, only 17 points. If I take 17 points, sorry, right. Of course not 17 points, 17 samples, very good. 17 samples, that means 17 times I am picking 2 points each, 2 points each time. Then 90% chance that even if there is 50% outliers, so that is the worst. More than 50% means the other model would be the winner anyway, right? And some other model could be winner. So for 50%, if there is 50% outlier, if I take 17 points, I am going to get the correct fit with 99% probability, quite high. I cannot expect more, right? So you can see this line is not growing that fast. It is kind of 2 times or like not more than that, right? Polynomial growth. But now if you see the other direction, if the S increases, how quickly those things get changed. So if I take it for 5%, you won't probably see it, but you can see what rate it is growing. It's also looking like it is also 2, but here every time the number is getting double. And what is that growth called? Exponential growth. So the things is growing exponentially.
Sir, could you please explain this table once more? S is the number of samples. S is the number of samples.
So two things, S is the for the line, we are talking about the 2. Very soon we will see actually about 8, S would be 8. So there will be, we need to match 8 points. 4 points from one image, 4 points from the another image, that would come very soon. Probably after the midterm, but it will come. But right now we are talking about the very most simple thing, 1 point cannot fit, so SS2 is the very simplest thing fitting a line. So I am talking about that for the SS2, and this is the outliers. How many bad points you have? 5%, 10%, 20%, 25%, 50%. So the more number of bad points you will have, the more number of samples you need to take to get a good point. So this is the same algorithm. At least 1 point in the outlier is this. If the S is high, then the probability of having at least 1 point in the outlier would be high. I do not want that, so that means I need to take more n to compensate that. I need to take more number of samples to compensate that, correct?
So, what are we doing when we take S equal to 7 or 8? Means how we are selecting S?
S is we are just putting these numbers here in this formula and getting this result. Okay? Clear? Even the brain is working. Okay, so this is the thing. So which one is bad? S. So what is the problem here? What is the good thing about it? Is very robust to outliers, because outliers, if there is even 50% outlier, I don't bother much. My algorithm is robust enough right now to handle all those outliers. Applicable for larger number of model parameters, then half transform. We can already have seen that 8. Half transform, what is the worst thing that could happen to half transform? The number of parameters, if that got increased. Remember, for 2 I just have a grid, for 3 I need to have a 3-dimensional grid. The voting becomes even worse than this. Here also the S is not that bad, not that good, but still better than half transform. Half transform is terrible. And if you run the code, write project 2, the very small, then you will see that if whenever you are varying the R, it is going to take huge time. You are working on that, right? Okay. So you will just see that how long it takes whenever you don't know the R, only one parameter. So half transform is very bad in that way. Optimizing parameters are easier to choose than half transform, because all we are going to do is some threshold. You are still calculating the error, but you are checking that if the error is within a bound or not. Okay. Now, what is the bad thing? Computationally, because if the S gets increased, your problem is again becoming exponential. So that is the bad thing. And as you can see here, if the outlier is less, you do not need to worry much, but if the outlier is high, things become very terrible with more number of S. So if both these things becomes high, with the fraction of the outliers and the number of parameters, whenever it grows increases, the model performs very not performs badly. You need to take many more samples, computationally expensive, and not good for getting multiple fits. So one time whenever you are running, you are just running it for the line, only one line, not multiple lines, because then again the vote will get split. Okay. What are the common applications? One is the image stitching. What is the image stitching? So those things will come soon. Actually, I have 2 images I want to put superimpose with one with the other. For that one, as I am telling, the camera might move, got changed, and all those things can happen. So the rotation, many other linear like perspective changes also can happen. Whenever I put that 2, I need to find out what happened between these 2 images. Okay. And fundamental matrix, I have just kept the slide here. We did not go over the fundamental matrix now. It will come later. But there also you can see that the RANSEC would be very useful. Okay. So now we have learned that RANSEC, how to use the RANSEC for line fitting. But no, that is not our purpose. Our purpose is to how can we do a good fit using find the best alignment. Okay. Right. by that algorithm we have talked about. Oh, why don't have that slide? So the algorithm talked about, okay, this can have the best match here, this point can have a best match with this point, oh sorry, this point can have a good match with this point, but I found out, okay, this point is matching with this point. So that is again an outlier. If you have some outlier like that, again RANSEC can be used to fix that problem. Okay. So all you are going to do is, in that case, that the same idea of the RANSEC for all those matching points, you are going to run RANSEC and you will see that which matrix manipulation is giving you the most accuracy. Linear transformation we talked about today, 2-dimensional linear transformation. How many points are there? How in the matrix? 4 points. So that is giving you the linear this one. We will see actually for the translation you need two extra. So that would come soon. So sometime you may need to have the six parameters you need to match. So whichever fit, like you have all those matching. Now whichever fit will give you the best match based on the RANSEC, you just tell that, okay, this is my final fit. I'll probably have some output soon. Okay, so let's see. Now we are talking about, so all we right now want is a global transformation. What is a global transformation? The matrix. Right now it is all about the matrix. Which matrix? The transform matrix. And we will see how does the transformation matrix, that is why we actually shown you the very first part, that how those looks like. So difficulty is, noise typically is 1 to 3 pixels, which is less. Outliers are often high. If it is high, it cannot, the problem becomes hard. And many to one matches or multiple objects. I need to detect multiple objects. So now actually let's talk about the alignment. Whenever I am aligning one image to the other, what are the transformation that can happen? So the same idea of the video lecture we have seen today in the morning, or not morning, at the beginning, the same thing. So if I have this, an image, and I stretch this image like that, so some transformation happened. That move point was here, right now it is here. Okay? So transformation T, so I want to find out, okay, what transformation happened. This is my parameter now, this is what I want to find. Earlier we were talking about a different problem. There I was giving you the T and I was telling that, okay, if I give you this transformation, where this particular point will go. Now the problem is I have the input point, I have the output transform points, and I am now looking for what is the transformation that happened. So I am looking for this T. So if I write this, I can write it down this, or I can just write multiplication, P bar is equal to T multiplication by P. Most of the time it will be multiplication, but we will see that there are some other times it will not be. So transformation is a coordinate changing machine. Clear? So whenever we are talking about the global transformation, that means for one point, whatever the transformation, it is the same for any other point. And also it can be explained by only a few numbers using parameters, as again for the rotation only 4 parameters. Okay? So now let's see. So how can you do that for the linear transformation? The transformation, and remember again, if you remember the linear transformation, we can represent T as a matrix, like I can write it down this. But are all the transformation linear? What did the video say? So we told something that very easily, origin should not move, and another thing is equally spaced. And very quick check is a line would be a line, no, not a curve. If it is a curve, it is no longer a linear. Line should be a line. That clearly easily tells that it is a linear transformation. The equally spaced, all those things violates that main thing. Line won't be any longer a line, right? So if it is the case, then you can always write P bar is equal to T multiplied by P. T is your transformation matrix. Connect to the video, whatever we have seen. That means this T is nothing but how the unit vectors are getting changed. Okay?
If we take two photos of same object, then the transformation of the two images will always
would be
will always be linear. If you take two photos of the same object.
no, it won't be. So we are seeing some simple example. Later will be more complicated. Perspective changes. Right now, if I take it one from here and another from there, no perspective change would happen. But later, I can take from here another. I can take from the sample, the side. There more changes would happen. So number of this. So we are talking of the S, right? The S will be higher. Number of parameters you need to feed would be higher. Later we will see that we will go to the until 8. 8 points we have to match. But the algorithm would be the same because right now you know the ANSEC, so you can use it for any algorithm, any model. Okay? So clear? Now see, if I have this original image, these are defined linear transformation. One is the translation. What is happening? Some points move to the right. Rotation, the whole things got rotated. Aspect ratio. Affine. Affine, what happened? Affine is kind of the shearing, and it is shear, and it can also have translation. Perspective. So perspective we are not covering right now because for perspective you need to have more parameters. Not 4 is not enough. Okay. So scaling. What is scaling? Scaling coordinate means if I have this, I am going to make this. Okay. So multiplied by 2. Can you tell me the T for this example? Let us see if you are getting it or not. The T matrix, how the T matrix would look like for this scaling. Tell me the number. Yes, you can see that also, no? 2, very good. Or if you think about the way you have seen, it is kind of like this. X and Y, right? X is 2, 0 instead of 1, 0 and 0, 2 instead of 0, 1. But diagonal is 2, 2, correctly said. Okay? Clear? So it is a linear transformation. Again, can you see that how can you use the ANSEC for that? If I give you two images, one is a zoomed in version of the other, then can you use the ANSEC? Found some point here, you found some point here. All you are trying that time is fitting 4 points. Take some samples, some good samples, and then they all will match to this algorithm. Clear? No? No, why? Whenever I am going to fit some points, in ANSEC what do you do? You just take one point, and this point and this point. How do you transform? You found out 4 points, and you want to find their like which transformation matrix? Okay, not 4 points. For this one, how many points you need? I need 1 point scaling, right? So 1 point. For scaling, how many parameters you are fitting? Two parameters. For fitting 2 parameters, how many points you need? How many points you need to fit 2 parameters? At least 2. 4 points or 2? You just need 2 points. Origin is same, right? So if I have a point at 2, 3, actually I need how many points? I need just 1 point in fact, because I am just fitting 2 parameters. So 1 point cannot give me 2, so 2 points. So 2, 3. So I am saying that I am going to the 4, 6, and another point probably. 2, 3. From there I am going to 4, 6. So this one pair of points is good enough to find out the scaling, because we are assuming no other transformation, right? So no transformation, no rotation, just scaling. Origin is fixed. So this pair, that one pair of point is good enough. You take one pair of points and calculate some using the RANSEC. You calculate what is the corresponding matrix you are getting. You are probably getting something like alpha, beta, 0, 0. 0, 0 will be there because it is scaling. This is a transform based matching, this one, right? Then you just take the vote. Okay, this alpha and beta, whatever you are getting, how many other points are acting to that? In this way, you keep on taking some pair of points, matching pair of points, and just do that. Clear? Clear? So, this is another scaling. X is 2 multiplied by 2, y is 0.5. So, the matrix is 2, 0, 0, 0.5. Okay? So, how can I write it down this? This is scaling matrix, x bar is equal to x, y bar is equal to by, that means in matrix notation this. You have actually told it correctly. Okay? We don't have much slides, so we will actually just finish it. Okay? So, scaling is done. Rotation. What do you think would happen to the rotation? X and y bar. So, I can write it down in this way. I'll just go back here. Okay. So, this rotation is, I had these xy points. After theta rotation, I went to the x bar, y bar. Okay? And this is what I got. X bar is equal to x cos theta minus y sin theta, y bar is equal to x sin theta plus y cos theta. Is it very obvious? If it is not very obvious, you can just do, I have just given you this part also. X equal to r cos theta, y equal to r sin theta, x bar is equal to this. So, this thing I am breaking, substitute I am getting this. Okay. Now, what is the matrix, transformation matrix? Cos theta minus sin theta, cos theta. Very good. So, that is the R I got. How many parameters I am fitting here? 1. So, again, how many points you need? Only one pair of points for RANSEC. Okay. Okay. Okay, good. So, what is the invert? So, this would be useful again later. So, if this is the, okay, from there by rotating by this matrix, I can go to this new, okay. So, if this is the point, by rotating to by this matrix, I can go to this new coordinate. But now, how can I go from there to there? Inverse. So, the inverse is the keyword. So, if I take the inverse, which is actually nothing but the transpose, interestingly, I can go back to the earlier one. Okay. Some other, now I should just show you some other one. So, scale you have already seen, diagonality. Shear is this. It is into both axes actually. So, last time I shown you like that. So, if I have like that, I can do it like this, right? Also, I can just do it like this. Like that also, right? So, both axes I can go. So, this is the way of doing. But if you now see what is happening, x is going by x, whatever is there, and some component of y. Okay? Clear? Now, rotate I talked about. Affine transform is having more degree of freedom. So, it can, any combination of the translation, scale, rotation and shear, it can covers everything. Now, translate I did not cover. What is translate? You can say translate I have extra component Tx plus Ty. Now, very fun part. Until now, translate and affine, can you see that how that two things are different from others? One more column, right? Very good. One more column. And now the bad thing is actually, whenever I am doing this one more column and if I just have x, y, can I multiply? No, that means I need to increase the dimension. Okay? But then I can actually just apply, and you can see that because I want the tx and ty just to move. So the new parameter would be x, y as it is, but the whole point would need to be moved by something in the tx scale. So the tx is going to add just directly.
So what will be this in 3 dimension?
3 dimension would be little bit complicated. It will have one more parameter. Again, it will have 3 here, and it will be even bigger. Not going there right now, but we will go there. Don't worry. Okay.
So in case of affine, there will be
6 parameters to match. Yes.
and in case of perspective, there will be
8 parameters, not 9 actually, 8. Why 8? We will see again, that also we will see. Why not 9? 8. Okay? Okay? Huh? Okay, what is the difference between affine and translate? Listen, this is here. You can see that ABCD is there, ABCD is there, here it is 1, 1. So that means nothing else, it is no perspective, like nothing is getting changed, only some point is there in the next image, it is as it is, some different location. Right. It is having all the components. Affine combines everything. It is having the combination of translation, scaling, rotation, and shear. It can have everything. But still remember, a affine transformation line would be line, and actually it has another property. Parallel line would be parallel line. Okay? Perspective projection, as you have seen, right? This. Their parallel line won't be parallel anymore, but affine transformation parallel line would be still parallel line. Okay. So affine transform, I can write it down in this way. Now you can see that x and y, and I am doing this, right. So for the affine transformation, line maps to lines, parallel lines remains parallel line, ratios are preserved and closed under composition. So you can just keep on adding those things. But now the important thing, you can see that in this example, these versus these, all we are going to do is actually we are going to add a 1 here and 1 here. So we are calling this is a homogeneous coordinate. Homogeneous coordinate, do you know about that? Good. So homogeneous coordinate, again when it will come, we will just talk in more details. Just again, but what is the main purpose of this? Just for for making the math easier. One is not going to harm it. So this is a prospective transformation, this is projective transformation, this is the 1, and later we will see that you do not need this I, you can make it a 1 here. So there will be 8 parameters to match. Projective transformation. So this is the image where you can get the feeling how this forms. Translation is you have this thing, it moved there. Similarity is the same thing, is probably rotated. Affine is it can have this form of type of shape. Prospective is kind of like this.
difference between Euclidean and similarity.
Huh? Euclidean and similarity or Euclidean and similarity. Oh, you can see that one is scaled, another is not. Similarity, it is smaller.
So we can represent the scale to 1 though.
Hmm?
In Euclidean,
Hmm.
we can replace the s with 1. So they are kind of superset and subset of each other.
Superset or subset? Euclidean.
Similarity is kind of the superset.
Similarity?
S equal to 1 there.
Here, yes, it is. You can think about that. It is the superset. But why? Like okay, the rotation. It is multiplying it to the rotation. So
If we are s equal to 1,
similarity is the superset because here it is S is 1. Yes. In that way, many things you can tell actually many things. Like the projective is the superset of all. Right. Okay, so probably we'll stop here today. It's already quite something. So next time we'll see. We'll just talk the same thing. How can you solve for translation? Again, we are for, but we'll see that next time. We have how many? Actually, we have only 4 slides. Should I finish? No. I will not finish it because next time we will be in a little bit better mood. Until whatever we will cover in the next class. Whatever we covered, so always that is the same answer, right? How do we have it covered in the last? Yeah, so all that. 3 research paper, yes. See, you don't need to read all, just read the slide and whatever you are not getting, that means you should refer the paper. Okay? Whatever is written on the slides, you should understand that very clearly. Okay? Not all, actually it is not the whole thing, some part of it. Who were not there last time? The tutorial session? So just if you are not there, just let's put a cross there. Let's just put a cross. You were there last time, the tutorial? No? Who else were there?
Sir, I was not able to.
Only 2 of you were there.
Yes. Oh, sorry.
Howrah is there, and then Howrah you were present last time too, so you can sign here, all the 3.